Let's take a look at these example problems for lesson 2.4. So question 1, a sequence begins -4, 1, 6, and 11. Give the next two terms. What type of reasoning, inductive or deductive, did you use when solving this problem? So if we take a look at this, we are going to try to see if we have a constant first difference, right? That's sort of the pattern that we had been exploring in earlier in the unit, although certainly this doesn't have to be the case here. So if I go from -4 to 1, I'm adding 5. 1 to 6, I'm adding 5, and 6 to 11, I'm adding 5. So I do definitely usually start with that constant first difference, but sometimes it could be multiplying, it could be some sort of alternating, type of number. So start there, and then if that doesn't work, try something else. So as I can see, it has a constant first difference, so I know it's going to be linear. All I want to do is find the next two terms. So 11 plus 5 is 16, and then 16 plus 5 is 21. So what kind of reasoning did we use? We used inductive reasoning because we were taking a specific rule and we kept applying it, right? So we were using specific examples, and then we were continuing to generalize it. And so that's what happens in part B. Find a rule that generates the sequence. This is still inductive reasoning, finding that rule, going from something specific to something general. In this case, again, our constant first difference is 5, and so that means 5 times something, the n, what number term we're in, plus something is equal to the value of the term. So to do that, let's go ahead and pull, I don't want to use the negative, that doesn't seem very fun, so I'm going to pull 1. So this is term 1, and this is term 2. So when n is 2, 5 times 2 plus something has to have a value of 1. So again, this is the term number, what number in the sequence I'm at, and then the answer is the term value. And so if I do this, I get 10 plus something is 1, and then if I subtract 10, it's -9. So the rule that generates my sequence is 5n minus 9. And like I said before, usually what I do is I pick a value further down in the sequence and make sure it works. So in this case, let's do the fourth term. 5 times 4 is 20, and 20 minus 9 is 11, so that works. Then it asks us to give the 50th term. So the 50th term, right, that means n is 50. And so we're going to go ahead and do 5 times 50, and minus 9, 250 minus 9, 241. This type of reasoning is deductive because we are going from something general, 5n minus 9, to something specific, the 50th term. So I really like question number 2. It is a little bit more of a thinking problem and less maybe explicit in terms of what sort of strategy you need to solve this problem, as we saw in example 1. So we know that triangle ABC is equilateral. So this triangle here is equilateral, and sometimes it helps me to label. So that means that BC, AB, and AC segments are congruent. Is ABD equilateral? So is this larger triangle ABD equilateral, right? So if ABD was equilateral, again, that means this segment AB, this segment AD, and this segment BD are all congruent. Now, it doesn't look like AD is congruent to AB. It looks like it's larger, but we actually can't say anything about that. It is not labeled. And when we look at a figure, what I like to say is objects in the mirror are closer than they appear, which means when we read something, unless it's marked and labeled or given to us, we can't actually conclude anything about it. So AD could be the same as AB. We just don't know. They could be congruent. But we do know something about BD. And that's where we're going to apply our reasoning. Because C is in between B and D, and they are collinear, that automatically implies, right, that BD, the length of segment BD, is the length of segment BC plus the length of CD. And that's by segment addition. And again, even if CD is like the tiniest measurement, we can conclude that BD is larger than BC. Okay? So, since BC is also equal to AB, that implies that AB is smaller than BD, or BD is larger than AB. You can say it that way. So what I did there was a substitution step. I took segment BC and I replaced it with segment AB because I had them as equal down here, and then I could do a substitution step. And therefore, I can now conclude that BD is larger than AB. Therefore, triangle ABD is not equilateral because it doesn't have 3 congruent sides. All we needed to show was that 2 of the sides weren't congruent to be able to conclude that it wasn't equilateral. Now, to prove it was equilateral, we would have to then again do something with segment AD, but because we had a contradiction with the definition of equilateral early on, we didn't have to do that much. This is not as rigorous of a proof as what we had been doing when we proved that when an obtuse angle is bisected, it makes 2 new congruent acute angles. But this is a good kind of introduction to deductive reasoning. So again, what type of reasoning did we use to solve this problem? Deductive. And the reason why this is deductive is because we're taking general things, definition of equilateral triangle, segment addition. We're taking general things and we're applying it to this specific scenario. So question number 3 is just kind of actually asking us to do a little bit of what we did with giving good definitions, right? We had examples and we had non-examples, and then we had to take a good, then we had to conclude what a good definition was based on those examples and non-examples. And this, at the time, we didn't know it, but this is what inductive reasoning is. We are going from specific scenarios, specific qualifications and qualities, and we're then generalizing them overall. So let's take a look. What makes something a whatnot? As I'm looking at these different whatnots, I'm noticing that they all have 4 sides, even though there could be some extra shape in the middle. They all have dots inside of them somewhere, even though there could be something extra inside. And then they all have a squiggle on at least one vertex. So that is what I'm concluding right now is going to start to make my whatnots. Now, let's take a peek and see what is not a whatnot and make sure what I wrote here is accurate for what a whatnot is. This is not a whatnot. If I notice, it doesn't have any dots. So it does fulfill the last 2 parts, but it doesn't have a dot. So that's a good part of my definition of what a whatnot is. Here, it doesn't have 4 sides, and it doesn't have a squiggle on a vertex. So that reinforces this part. This one, it has 4 sides and it has a dot, but it doesn't have a squiggle on a vertex. So that's helpful. This is a pentagon. And so again, it's back to the idea of being 4-sided. It does have a squiggle on the vertex, so that's helpful. And then this one, it is 4 sides, has dots, has a squiggle on the vertex, but guess what? It is concave. So this reminds me that a whatnot is convex. So if I go over here then to my question, which one of these are whatnots? A is a whatnot. It has 4 sides. It's convex. It has dots, squiggle on a vertex. B is not a whatnot. It is circular. C is not a whatnot because of this extra squiggle right here that's not on a vertex. D is not a whatnot because it is a convex polygon. Or sorry, excuse me, concave polygon. It is not convex. It has four sides, and it fits the other parts of the definition, but it is concave, not convex. E is a whatnot. It has the dot, it has the squiggle, it has four sides, and it does have extra pieces inside, but that's okay, right? This one had some extra stuff. This one had a circle inside. F is also a whatnot. All the vertices have squiggles. There's four dots. There's extra lines inside, but there's nothing about that in our examples and non-examples that preclude that, and not including that. So again, our whatnots were A, B, and F. So there we go. That concludes lesson 2-4. Great job. And again, reach out if you ever have questions.